In this video, we want to give a demonstration of Stokes' theorem. We proved it in the previous video that this general expression, here we have a three-dimensional vector. We're taking the line integral about a curve, and that curve encompasses some solid figure. And this is equal to the surface integral of the curl of that vector and taking the dot product of that with a differential area vector. And again, we proved this in a previous video. Now I want to give a demonstration of it. And here's what we have. We have the equation x squared plus y squared plus z squared equals 4, but we're considering only the positive part of z. So this will be for a hemisphere. So in the xy plane, there will be a circle of radius 4. The circle would look like this. And we're going to take the line integral about this circle. That's what this is. And see if that is equal to the surface integral for the entire object, for the entire hemisphere. Probably it will take all this video just to do this part, and then in another video we'll compute this and see if they come out equal to each other. So here is the vector field, and when we have a line integral, it's in general in this form. But now we're taking our line integral just in the xy plane, so there won't be any z component to it. But the line integral will look like this. It will be 2y dx and then we will have another component of this, which will be minus x dy. Z is 0. We're just down here in the xy plane now. So we want to take the line integral then about this circle. X squared plus y squared equals 4. Now, here we have an integral then where we have dx and dy. But we can use our figure or use our equation here to say, well, x, we can express that in terms of y. That equals the square root of 4 minus y squared. And dx, we can express that in terms of y. This would be 4 minus y squared to the 1/2. I guess we'll write it like that. So dx, that will equal 1/2 times 4 minus y squared to the minus 1/2, and then minus 2y dy. So dx will equal minus y dy over that square root. So let's write it like that then. We have minus y divided by the square root of 4 minus y squared dy. So now for our integral, here we have y times dx. Dx is expressed in terms of y, minus x. Here x is expressed in terms of y times dy. So can rewrite our entire integral in albeit terms now expressed of y and dy. So it's going to be the integral 2 times y times dx, and dx is this, so we have minus y divided by the square root 4 minus y squared dy. Get this into better focus. So 2 times y, dx is this right here, except this we want to be a square root of. The square root of 4 minus y squared, like this. And let's make this integral sign a little bit neater. So it'll be like this. Now we have this part, minus x, but x is that square root, so we have minus the square root of 4 minus y squared times dy. So our line integral now is expressed in terms of the variable y and dy, and we're doing it now considering this over this circle. So you can see that y goes from minus 2 to plus 2. That would be half that circle. So we could just say it like this. Y goes from minus 2 to y equals plus 2. From minus 2 to plus 2. Then by symmetry, we can say for the whole circle, it will be 2 times that integral. So here's the integral that we've got to work with. And let's see. This will equal 2. And we have to combine these together. So let's see what we're going to get. We will have 2 on the outside. Y goes from minus 2 to plus 2. Here we have minus 2y squared divided by this square root 4 minus y squared minus square root 4 minus y squared, and this is all times dy. So our line integral now has this form, and we can put this over 1. So we will have from here then, on top, minus 2y squared then minus this times this, so we'll have minus 4 minus y squared divided by this times this, divided by the square root of 4 minus y squared. Of course, this is inside of the integral sign. Y goes from minus 2 to plus 2, and this is times 2. So that's our expression so far, and let's see what we have. We have, looking at this then, minus 2y squared minus 4 minus y squared. So this will be minus 2 plus y squared. They have a minus sign, so this will be minus y squared minus 4. Of course, we have a dy here. So our numerator is minus y squared minus 4. So let's put this up here. Or if we want, let's put minus 2 out here, and we'll have y squared plus 4. So the integral that we have to evaluate is going from minus 2 to plus 2, y squared plus 4 divided by the square root of 4 minus y squared dy. Let's make some room, erase everything, and write this then at the top, and see how we can solve that integral. So we're going to erase all of this now. And we have this integral, minus 2. The integral y goes from minus 2 to plus 2. And we have 4 plus y squared divided by square root 4 minus y squared dy. So this is what our line integral is shaping up to. All we have to do now is solve it. Now, usually when we have an expression where we have some constant minus a variable, that sets us up usually for a trig substitution. And we know that cosine squared plus sine squared equals 1. So 1 minus either one of these would be a constant 1 minus some variable, either the sine squared or the cosine squared. And that's this general form, a constant minus a variable. So let's factor the 4 out of this. So that will be 4 times 1 minus 1/4 y squared. That's this with the 4 factored out. Then we'll take it to the outside of the square root sign, so we'll have a 2. So this will be, remember this is under the square root sign, take that out and we will have 2 times the square root of 1 minus 1/4 y squared. Now we should be set for a trig substitution. Let's try it like this. We'll say let y we have this 1/4, so let's say let y equal 2 times the sine of theta. So that this squared will be 4 divided by 4, that'll be 1 sine squared theta. We'll get to that in just a moment. And if we do it like that, though, dy, we have to consider that, that will equal 2 times the cosine of theta d theta. So let's see what our integral looks like. You can have this, we have 4 plus y squared. That'd be 4 sine squared theta. Divided by, now here we have minus 2 divided by 2, so that's just minus. Then we have the square root of 1 minus 1/4 y squared. That's 4 sine squared theta, so this just be 1 minus the sine squared of theta. 4 divided by 4 is 1. Now dy, that's this, 2 times the cosine of theta d theta. And we're going to have new limits here, but for the moment we'll ignore those. We'll come back to these in a moment. This is the cosine. 1 minus the sine squared of theta is the cosine squared. Take the square root of that. So this and this cancel. We can factor the 4 out of this. You have 4 times 1 plus the sine squared of theta. 4 times 2 is 8. So with our trig substitution, we get minus 8, the integral of 1 plus the sine squared of theta d theta. So our line integral now has this form after we did our substitution. Now, to handle this part, remember that cosine squared theta, I'm going to try this approach, plus, not this is the only approach, but cosine squared theta plus sine squared theta equals 1. And the difference of them, the cosine squared theta minus the sine squared of theta, that's the cosine of 2 times theta. So if we subtracted this minus this, we would have that 2 times the sine squared of theta will equal 1 minus the cosine of 2 theta. Or the sine squared of theta will be 1/2 here minus 1/2 the cosine of 2 theta. That's the sine squared of theta. We have 1 plus the sine squared of theta. So we add 1 to this side. 1 plus 1/2 is 3/2. So for this, 1 plus the sine squared of theta, we can substitute this in, and that will then be our new integral, and that we should be able to integrate. Let's see what we have. We'll have minus 8. We still have to consider our limits. This is 3/2 minus 1/2 the cosine of 2 theta d theta. Now this minus 8 times 3/2, that's minus 12. So we have minus 12 the integral of d theta, and then minus 8 times minus 1/2, that's, oh, this should be the cosine of 2 theta. 1/2 the cosine of 2 times theta. It's important to have that written correctly. Okay. Minus 8 times minus 1/2 is plus 4 the integral of the cosine of 2 theta d theta. This would just be minus 12 times theta. The integral of the cosine is plus the sine. With this 2 theta here, that integral of cosine 2 theta d theta, that is 1/2 times the sine of 2 theta. So this 1/2 times 4 is 2, so we have plus 2 times the sine of 2 theta. So what we did was, our original integral, after some manipulation, our original line integral was this. Made a trig substitution. We got these expressions, and then we got this answer. So we're going to write this now up at the top, remembering that our trig substitution they made originally was this. We don't want to erase that. So you have minus 12 theta plus 2 times the sine of 2 theta. And hopefully we'll be pretty close to getting an answer for this. So we have minus 12 theta plus 2 times the sine of 2 theta. Now, here was our substitution right here. So theta, that is equal to the inverse sine of y over 2. And from here we have minus 12 times theta. So here for this part, it's minus 12 times the inverse sine of y divided by 2. And remember that y had limits on it from minus 2 to plus 2. So that's from this part. Now here we still have to consider this, the sine of 2 theta. Now here's where it's useful to draw a triangle. Let's go to here. We know what theta is now. We don't need this anymore. So the sine of theta equals y over 2. So we draw a triangle like this. This is theta. The sine of theta is equal to the sine, well, the sine of theta equals y over 2, which is the side opposite divided by the hypotenuse. So this side here is 4 minus y squared. Now, the sine of 2 theta, remember what that is equal to. The sine of 2 times theta, that equals 2 times the sine of theta times the cosine of theta. Okay, well the sine of theta, of course, is y over 2. The cosine of theta, that is this divided by the hypotenuse. So the sine of 2 theta will equal 2 times y over 2 times the cosine of theta. That's this, the side adjacent, divided by the hypotenuse. That's 2. Now from our expression, we have 2 times the sine of 2 theta. So multiply this by 2, this becomes a 4. So the sine of 2 theta is equal to this expression. So we have plus, and we'll have 4 times y over 2 times the square root of 4 minus y squared over 2. And we're going to write this right here after we erase some things and make some room. So let's see. I'm going to erase this. We have plus 4y over 2 times this, square root of 4 minus y squared. Divided by 2. This is 4 times y over 2. And y goes from minus 2 to plus 2. Now let's get rid of this. So we have then that the answer to this integral, minus 2 times this integral, gives us this expression. Now here if we put 2 in for y, that's 4 minus 4. If we put minus 2 in for y, that's 4 minus 4. So this just gives us 0. So we can get rid of this part. And here this equals minus 12 times the inverse sine. Y is 2. That's the inverse sine of 1. minus the inverse sine. Y is negative 2 of negative 1. So the sine of what angle is 1? That's 90 degrees, or pi over 2. So you have minus 12 times pi over 2. And the sine of negative 1, that would be minus 90 degrees, or minus pi over 2. So we have minus, and this is minus pi over 2. Or this would be pi over 2 plus pi over 2 is pi times minus 12. This equals minus 12 times pi. So finally, there's our answer. It took a while to get it, but that is what the line integral is equal to. Now, in the next video, we have to take the surface integral with our hemisphere and see if we get the same answer. That is, see if it comes out to be equal to minus 12 pi, as Stokes' theorem says it should. So join us for the second half of the video, and we'll continue along here with our problem. The playlist for all these videos is at the website digital-university.org.